now that we've gotten the basics of momentum out of the way, we need to start looking at how things interact. And nothing ever acts by itself in a vacuum. So what we're going to look at now are how two objects react. And what we'll be looking at a little bit is, first off, there's going to be this idea of conservation of momentum. Okay, remember back to chemistry, and you dealt with a couple things there. There was conservation of mass, conservation of energy. Okay, you realized that in a chemical reaction, all the mass you had before had to equal all the mass you had after. The same thing is true with energy. Well, now what we're up to is the conservation of momentum. Okay? And, just in the absence of an external force, the total momentum of a system remains unchanged. Okay? Basically what that means is all the momentum you had before a collision or an interaction has to equal all the momentum after. As long as it is in the absence of an external force, there's nothing outside influencing it going to change us up. Okay? It's in the absence of an external force. Okay? And from our point of view, if we want to keep it easy, this law applies to a closed system. Okay? It's got to be closed. Okay? You can't keep having these extra variables in. Okay? Usually, for us, it's going to be two cars colliding or two somethings colliding. Now, we can make it more complicated and have 5 or 6 or 10 or 20 interacting, but we're going to keep it with two. Two objects, two cars, two people on rollerblades. But in fact, do you think if we talked about, a car wreck out on 75, well, you think the law of conservation of momentum is going to apply? Well, yeah, it is. Okay? But when we have our two cars, we have to exclude all these other people and all the other masses. We don't want things to change. We're going to keep it relatively simple. Okay? Didn't I just write on that one? Conservation of momentum, again, closed system. Here, I'm going to go to the next one. I don't know why I had to. Think about this. Let's say two balls with the same mass collide. We got an 8-ball. The 8-ball's up over here somewhere. We got an 8-ball and a 3-ball. Okay? The 3-ball's just sitting there. Things to think about. Which ball has the greatest original momentum? Who's got the momentum at the beginning? Okay? Who has the greatest momentum change? And which ball has the greatest impulse? Remember, we basically have to compare the mass times velocity of the 8-ball. That one's rolling that way, right? And we have the mass times velocity of the 3-ball. Okay? Key phrase in here. The 3-ball's just sitting there. What's its velocity going to be? Okay? Think about your answers for a sec. Which ball has the greatest original momentum? Which ball has the greatest momentum change? And which ball has the greatest impulse? What do you know about the change in momentum here and the impulse? What do you know about those two quantities? Hopefully, you know a little already, and you can kind of think about your answers and figure things out and without even having to go roll a couple balls at each other, right? So which ball has the greatest original momentum? The 8-ball, right? The 3-ball's not moving, so its initial velocity is 0, so it has no momentum. Which ball has the greatest momentum change? Okay, we got an M, delta V here, okay? They both have the same momentum change. The 3-ball gains momentum that the 8-ball loses, according to this, right? You can do the numbers and we'll see. What if the 8-ball had 10 times the mass? The same thing. The conservation means one gains, one loses, and they need to be the same. Which ball has the greatest impulse? Okay? They have the same impulse. Why? Because they have the same change in momentum. Okay? That impulse is that change right there. Now, when we start talking about collisions, we're going to talk about two different kinds. The first one is called elastic. Elastic is when objects collide without being permanently deformed and without generating heat. You know, we'll put in here no loss. How do you spell loss? Loss of energy, okay? And this way you have, you know, on paper you have a perfect transfer of energy, you know, from one to the other, or in this case, transfer of momentum. Two billiard balls colliding, right? You got the cue ball rolling into an 8 ball, right? You got a mass and velocity here and a mass and velocity here. You can think of, you know, bumper cars. You know, go to the bumper cars at the fair. You know, your older brother and sister probably be gunning for you. Why? Well, they like colliding. All of their momentum gets transferred to you if it's a nice good hit. Two kids running, bumping into each other. They bounce off of each other. Okay? You know, we'll look at a couple of situations for elastic collisions. Okay, remember there's no loss of energy. I was just gonna put in a couple examples for you. You could do something. Whoop, that didn't work. Let me get us a color here. Okay, you know, if you had like bowling pins, I can't draw bowling pins very well. And there's your bowling ball. It's got a smiley face on it. Okay, you got a mass and velocity here. You got a mass and velocity here. Okay. What happens then? You get the bowling pin going that way. You get the ball going the other way. Okay? The other types of things that could happen, whereas if we had like pool balls, we just have one at the same situation, right? You got a mass and velocity here. You got a mass and velocity here. Okay, these, you know, it may be a situation where if you've played pool, or, you know, if that's a 1 and that's a 2, okay, if you can transfer all the momentum directly, then number 1's going to stop. The other thing you might be able to think of is with cars, okay? With cars, there's no entanglement, it's just, you know, one bouncing off of another. I don't draw very well. There's a truck. Okay? And they might just be going at each other at the beginning, right? Might have something like that, right? Brings up a situation that we'll have to talk about in a little bit. But we have our mass times velocity here, and we got a mass times velocity here. So elastic collisions, there's no loss of energy, okay? And these things don't get tangled up. You know, if you look at the law of conservation of energy, what is it going to look like? Well, and we'll talk about it in a little bit more detail. We'll crunch some numbers. But what do you know about your before and your after? Okay? You're going to have to know that the before momentum has to equal the after momentum. Okay? The other thing that can happen is you get some type of inelastic collision. Two things are going to collide, but they're going to become tangled up or coupled together. I mean, this was a pretty nasty looking train wreck over here, but you might get a place where two freight cars hitting and continuing on. You might get a situation where a football player tackling another one to the ground. Okay? And what does this look like? If you become entangled, you know, we got a classic situation, right? This guy running at that guy. Okay? So, whoops, sorry, he's going to the right. Okay, so you have the before, and the after is what? Well, you could have it, if they're going down, going that way, because I made this guy look a little bit bigger, right? Okay? But we're getting entangled together, and both of them go the same direction. Coupled together, it's kind of like you could have it, the same type of a thing going on. If you have a train here, right? You got a mass and velocity, you got this moving, okay? Let's say at 5 meters per second. And then if you have a train car stopped, at 0 meters per second, okay? These trains have hooks on them, so quite frankly, they become hooked together, and now what are we going to do? They go off together. Are they going faster than your original 5, slower than your original 5? Just what are they doing? It's the same way when you become entangled, okay? How are we going to deal with that? Things you need to remember. If you get lost, the momentum before equals the momentum after. Period. No questions. Okay? So you're just going to have to take your two objects, work with that one. Momentum 1 plus momentum 2 before equals momentum 1 plus momentum 2 after. Think of the equal sign as being the collision, okay? And what we're looking at is simply trying to figure out, we'll try to figure out an end velocity or try to figure out an end mass or something of that nature. But the key thing is before equals after. Set those sides together. I think I missed my bottom part down here. Okay, here's your calculations continued. Use an elastic. There's your calculation, right? There's your before. There's your after. Okay? It's your two objects. Inelastic collision. What happened? They got coupled together, right? So our masses are going to get totaled. So remember, read the question clearly. Determine if it's an elastic or inelastic collision. Do the cars bounce off of each other? Do the cars get tangled up? Or kids, or people on skateboards, or whatever the case may be. Do they get tangled up? Do they bounce? Watch for your negatives. If you remember those problems on one of the page, if a ball comes in at 20 and goes out at 20, then you'll have to be looking at a change in velocity of 40. You have to watch your directions. If you make one direction positive, the other one has to be negative. Okay? Whoop. There we go. We'll try to get some problems up over the next day so you can kind of see what's going on. But that's your start. Good luck. Bye.